All right, so back into this algebraic modeling material. Last time, remember we were dealing with these exponential models. And the two most prominent models, the two models that we're going to use, one of them is the basic calculating interest model. That is where you're compounding m times per year or per any length of time. That's this top one here. The other model that is often used is the continual growth model, which is the P times e to the RT. That is continual growth happening all the time. So if you're increasing by 5% monthly, that's this one with the M. If you're increasing by 5% continuously, that's this one with the E. We've done a couple of examples. We did an interest calculation and a rapid growth population. Let's do another example. Now, this one is about plutonium-239. And it says its half-life is about 24,100 years. This means that the decay rate is about 2.88% compounded continually per 1,000 years. So it's, notice that our time frame here is per 1,000 years rather than per year. Everybody got that? So a T of 2 means 2,000. T of 5 means 5,000. Write an equation for the amount of plutonium-239 after T 1,000 years if you start with 200 pounds. So the first thing we have to do is just make sure that we're using the right equation. Because we're doing this continually means I need to use the A equals P times E to the RT. Okay. Decay rate is 2.88% per 1,000 years. And we're going to start with 100 pounds. If you start with 100 pounds, that means your P is going to be 100. And then the rate is 2.88% of decay per 1,000 years. And it says, make sure the T is in thousands. Now there's two things here. Because we're doing a decay instead of a growth, our R is going to be negative. So the R is going to be negative 0.0288. And then we're going to use T because our decay rate is per 1,000 and our time is in thousands of years. Is that all right? So just as a note, decay rate means to use negative R. So that's why we're using the negative 0.0288. It's a decay. Does that make sense? So growth's going up, it's going to be a positive rate. Decay is going down, it's going to be a negative rate. So I wanted to make sure we have a couple of those. Now, once we have that equation, we can answer questions like these. How much is left after 5,000 years? How much is left after 30,000 years? How much is left after 200 years? How much is left after 3,400? I'm gonna write all those on the board, but if you want to calculate those, go ahead and try to calculate those on your own. So we got 5,000, 30,000, 200, and 3,400. All right, let's go through these examples. Now, the key thing here is that the T we're using is in thousands. So when it says how much is left after 5,000 years, 5,000 years is a T of 5. Right? And so when I plug that in, I got about 86.59 pounds. Right? And whatever the other decay would have been. Okay, we start with 100 pounds, right? About 86.59 pounds of plutonium-239 remaining. And then the other, for those of you who don't know how it works, when you do decay, plutonium-239 changes into non-radioactive uranium-238, I believe. So whatever but you still have that much plutonium-239, and then the other part would be when it decays into, and I believe it's uranium-238. But might be wrong. Similarly, when we type in or when we try to find how much is left after 30,000 years, that's a T of 30. And the amount that's left is about 42.15 pounds. When we talk about 200 years, that's 0.2 or 0.2, right? That's not yet a full 1,000 years. So it's 0.2, and then you plug that in. And I got about 99.43. Again, that'd be pounds, but. Is that all right? And then lastly, after 3,400 years, that's a time of a T value, I should say, of 3.4. We just plug in 3.4 in for the T. Again, make sure you plug that in nicely in parentheses, all that stuff. And the amount we have left is about 90.67 pounds. That work? So each of those 4 problems just requires you to plug in a different T. Now later on in your math, how do I say? Later on, if you keep taking math classes, you'll learn to say, well, can we plug in for A and then solve and find T? And it turns out you can. We're not going to go over that in this class because that requires us to understand some things about natural logs that would just take too long. But it turns out you can plug in for A and solve for T as long as you're willing to use some natural logs and things like that. So, but again, that's not for this class. This class, I'll never have you plug in for A and solve for T. In this class, I'd have you always plug in for T and find A. In a problem like this, obviously. Oh, come on. All right. I want you to do one more on your own. This one. And then after you've created the model, figure out how much the account will be worth in 15 years and how much the account will be worth in 25 years. $15. All right, let me go through this. So because we're compounding monthly, we're utilizing that equation. The amount was 428,000 that was in the account. it was supposed to be compounding at a rate of 8%. So it's 8% compounding monthly. And so the equation looks like that. All right. And then the two time frame questions were, how much is this going to be worth after 15 years? And how much is this going to be worth after 25 years? When you take 12 times 15, you get 180. So if you're wondering where I'm getting that, well, actually, I'll just write it down this way. So the exponent's 12 times 15, which is 180. If you want to put it into the calculator. The amount you have after 15 years is going to be $1,415,362.39. After 25 years, the amount that you're going to have, oops, let me rewrite it, what I'm doing. So I'm taking 428,000 multiplying by 1 plus 0.08 divided by 12, the 12 times 25. So once I've done that calculation, I get 3,141,595.31. Is that right? So here's our model. And then we can use it to get answers. By the way, notice that we're talking about 15 years. You're ending up with 1.4 million. But those next 10 years, you more than double it, right? It goes from 1.4 to 3 million. So those next 10 years are really, really big. And if you remember what we talked about back in the investing chapter, we said the earlier you put in money to save for your retirement, and the longer you have to earn interest, the better off you're going to be at the end. Well, again, this is another, if you are only saving your last 15 years for retirement, that's a big difference than saving your last 25 years. I know we start with a big initial amount, but that's what it is. Is that right? Good. All right. Now, I'm going to mention something that does come up in real world applications. I'm not going to ask you any questions about it in terms of trying to create a model, but oftentimes what will happen in a real life situation is things will grow exponentially and then level off. So for instance, if you first introduce a new species into an environment, they might reproduce in an exponential way until they've used up the resources for that environment. And then their population sort of levels off. Okay. So if you were to introduce, I don't know, bison on, let's just take a state. It's a state in the West. Let's take Iowa, for instance. Let's pretend that the entire state of Iowa gets converted into a bison preserve. Well, initially, the population of those bison is just going to take off and grow like crazy. Up until they hit the point where they've essentially used up all the resources. And then their population would level off. Okay. Again, Iowa doesn't have any real big natural predators for bison, so that's why I chose Iowa instead of some state. That type of leveling off, where we grow exponential and then level off, is a logistic model. All right. And they're important for things like natural growth, but with a limitation. And they're also important when you take a look at certain types of statistical modeling. There's a certain type of statistical modeling that you do when you have yes-no type data, zeros. You have two choices in your data and use logistic modeling growth there too, but I won't get into that. But I just wanted to make you aware of that, because a lot of times people say, oh yeah, that's exponential at the beginning, and then it levels off towards the end. Okay, so I just want you to be aware of that there are these things called logistic models that look like exponential and then level off. Is that right? All right, so let's take a look at some quadratic models. We'll go through these pretty quick. We'll have a couple of examples probably. Remember, quadratic is this relationship between y and x, where our x is growing at a squared rate over time. If we have a decay, we just use a negative. Here's an example of a standard quadratic model. An object is launched at 19.6 meters per second from a 58.8 meter tall platform. The equation for the object's height, I don't know why they didn't use h, should probably use h instead of s. So they're using s for height. At time t seconds after the launch, it is this. I'm just going to use h for height. Is that right? So height equals negative 4.9 times t squared plus 19.6 times t plus 58.8. All right. Now I want to kind of point out some things because this is very typical for heights of objects thrown off of ideas. So you'll notice that the speed at which the object is launched, 19.6 meters per second, shows up right here with the t to the first power. So it shows up as the coefficient of t to the first power. You also see that this 58.8 meter tall platform, that shows up as the c. And then this negative 4.9 times t squared, that actually comes from your constant of gravity, your gravitational constant. All right. So that coefficient comes from gravity. This coefficient comes from the speed at which it's launched. And then this number comes from the original height. Or the initial height. Does that make sense? The initial height, the speed, and the gravity. And in general, that's the way it's always going to be. The c is the initial height. The b is the speed. And the a is your constant involving gravity. When I say A, B, and C, I'm referring to this here. So your A comes from your gravity coefficient, your B comes from the initial speed, and the C comes from the initial height of the object being tossed. That's generally how that's going to work. Does that work? Now, we can ask questions about this model now that we have it. Like, how high is the object initially? How high is the object after 2 seconds? About 4 seconds. About 6 seconds. I'm writing that down on the board. If you have your notes already, print it out. You don't have to write that, obviously. Okay. So when we say how high is this initially, all we're saying is what's going to happen at t of 0. We kind of know what's going to happen at t of 0. Even before we start, because it said that the initial height. We launched it off of a tower that was 58.8 meters tall. Right. So the initial height is 58.8. That's just what you get, because that goes to 0, that goes to 0. After 2 seconds, well, we'll just plug in a 2. And for the t value. Say negative 4.9 times 2 squared plus 19.6 times 2 plus 58.8. I ended up with a height of 78.4 that's it, meters, excuse me. Everything was in meters. Meters and seconds here. After 4 seconds, do the exact same thing, but now with 4. You can actually just go back up and change everything you typed in from a 2 to a 4. And you get a height of, once again, 58.8 meters. And then after 6 seconds, you get a height of 0 meters. Is that all right? Now, I want to say 2 things about this. The first is just realizing what's going on, right? We have a tower and we are launching an object off the tower. For the first 2 seconds or so, it looks like it's going up, and then it's going to come down, and after 4 seconds, it gets back to even with the height of the tower. And then eventually comes and hits the ground, right? So that's what's happening. So the first 2 seconds goes up, next 2 seconds going back down, then after 2 more seconds, it's hitting the ground essentially. So that's what this tells me. The other thing I want to say is I mentioned just a second ago that everything was in meters and seconds. That's basically true. The heights, the initial heights and all heights are in meters. The speed is in meters per second. And then the gravity is in meters per seconds squared, where the seconds are being squared. The reason why we have to have everything in like meters and seconds is so that all these terms can combine into meters when you multiply things out. if you think about this, the second squared, time is also in seconds. So time squared is like second squared, they cancel each other out, multiply. One's multiplying by second squared and the other's dividing by second squared, so cancel each other out. So the gravity coefficient is always meters per second squared, or some other measurement per some other time squared. Is that right? Make sense? All right. Good. Now let's create an equation that results in a quadratic. So in example 1, we were just given the quadratic. Here, we're going to try to create an equation. And a lot of times, these quadratics will pop up when we're multiplying two different values, and each value has an embedded variable in it. Then you have variable times variable and you get a quadratic. So this person, Kyle, works at a nonprofit which buys bulk food to distribute to kids. Current price is $40. And they're buying 50 pallets. So that's $40 per pallet of food. And they're buying 50 pallets of food. The cost is going to go down $2 per pallet of increase. Up to 60 pounds. Cost goes up $2 per pallet if you order less, all the way down until you get to 40 pallets. So, does everybody understand this? Right now we're ordering 50 pallets. If I order 51, then the cost is going to go down by $2 per pallet. If I order 49, the cost is going to go up $2 per pallet. Does that make sense? And we want an equation for the total cost spent above or below 50. So the cost is changing by $2 per pallet. It's right now at 40. By the way, the total cost, hopefully, pallets is going to be the number of pallets that we order times the price per pallet. Everybody agree with that? Does that make sense why the total cost is what it is? All right, so right now, we're spending $40 per pallet while we're buying 50. So right now, the total cost would be 50 times 40, which I believe is 2,000. So we're going to create an equation for cost. I'll just write C for cost. Now the number of pallets, it tells me to use N as the number above or below 50, right? So we'll assume that a positive N means I'm gonna add more pallets. So like N equals 1 means I'm buying 51 pallets. N equals 3 would mean I'm buying 53. Does that make sense? And then if it was a negative N, I'd be buying less than 50. So the number of pallets is going to be 50 plus the additional pallets that I'm ordering. And if I want to order less, I'll just use N as a negative number. That's the number of pallets. Right now it's 50. Let's increase it by a couple or decrease it by a couple. Now the price per pallet is going to go down $2 per additional increase. So if the price right now is 40, it's going to go down $2 per pallet of increase. And that's my cost equation. Now we could simply just stop there and use this equation. In fact, we might do that once we get to actually making the computations. But I want to show you that this cost equation is in fact quadratic. Because if you were to try to expand this and take this number times this number, you have to multiply the polynomials together, and that causes you, in this case, since we have a binomial times binomial, to FOIL it out. You've probably heard the term FOIL. That's take 50 times 40, which 2,000. Then take 50 times negative 2n, that's minus 100n. Then take n times 40, that's 40n. Then take n times minus 2n. N times n is n squared. I'm just going to rewrite that so that the n squared comes first. That's negative 2n squared. Then these two are actually like terms. So if you have negative 100 and a positive 40, you actually have negative 60n. And then you have plus 2,000 there. Is that right? So you can see that this is quadratic in nature. That's all I'm trying to do with the multiplication, is to show you that yes, when you have a variable here and you have a variable here, when you multiply them out, you're going to get an n squared. You're going to get your variable squared, which is a quadratic. Does that make sense? Now, I do want to note that this said up to 60 pallets and then down to 40. So n technically can only be a 10 swing. Does that make sense? So technically this only works when n is between negative 10 and positive 10. All right. So on some problems you may see, oh yeah, this only works in this range. In our case, negative 10 to positive 10 is the only range that works. I want you to plug in a bunch of n's to see what the total cost is when n is negative 10, negative 5, negative 2, 0, 2, 5, and then positive 10. Go ahead and try to plug those in. All right. Now, it doesn't matter which equation you plug that n into. You can plug the negative 10 into here, or you can plug in the negative 10 into this one. It doesn't really matter which one. They're going to give you the same answer. These are actually the two, let me rephrase this. These two equations are the same thing, right? Just one is multiplied out, the other is not multiplied out yet. So whichever way you want to do this, you can. I use that one because a lot of times if I plug in negative 10, it's easy to say, oh yeah, that's 40 in my head. Plug in negative 10, oh yeah, that's 60 or whatever it is. When I did this, when n is negative 10, the total cost is 2,400. When n was negative 5, I get 2,250. When n was -2, I get 2,112. When n is 0, I get 2,000. That's the 40 times 50 case. When n is +2, I get 1872. When n is +5, I get 1,650. And when n is +10, I ended up with 1,200. So you can see that in this case, if you ordered 10 more pallets, your costs would go down and you'd have more, in this case, food to distribute. All right. And if you were working at a nonprofit that was distributing food, that's probably a good thing, having more food to distribute at a lower cost. Now, this is obviously a hypothetical scenario, so a lot of times there's balancing points and things like that. But yeah, this one was interesting. Any questions about quadratic models? So we have the ones like the heights, they're given to us, and then the ones like the buying in bulk food stuff. That one wasn't given to us, but we can create it when we have two things being multiplied together. Now we have two more sections in chapter 7. One is on rational models, and one is on what we call given models, or previously produced models. And in this class, when we're dealing with rational models, I will give those to you as well. All right? So they're kind of interlinked, these rational models and these previously produced models. Let's start with rational models and why we would care about rational models. In mathematics. Well, a lot of times rational models in general can have upper and lower limits. All right. And that gives a sort of bounds. So imagine I was using the last problem and I said, well, I will sell pallets of food and I'll give you a discount for ordering more. Well, at a certain point, I can't give you 100% discount, right? So maybe I say, well, the lowest I'll let this go for is $20 a pallet, and that'll be my lower limit. And the most I'm going to charge anybody is $70 a pallet. So my price is between 70 and 20. Well, a rational model can accommodate that. It can start with a price of 70, go down to a price of 20. Now, again, we're not going to produce these rational models or rational functions in this class. In this class, I'll tell you them. In terms of the types of rational models I'm going to give you in this class, I'm always going to have linear divided by linear. That is not a full extent of all rational models. Anytime you have a polynomial divided by another polynomial, that's a rational expression. If you have a function that's equal to polynomial divided by polynomial, that's a rational function. But the types we're going to look at in this class are always going to be linear divided by linear. So ax plus b divided by cx plus d, where a, b, c, and d are just real numbers. All right. So let's pretend we're at what's called customink.com. You guys know what this is? This is a website in which you can design a t-shirt. And then you order that t-shirt from the website and they send you as many as you want. And if you order 10 t-shirts, they're going to give you a certain price. But if you order 100 t-shirts, they're going to give you a little bit better price per shirt. Okay. There's lots of websites that do this. For Imprint is another website that does this. Now, let's pretend that for a certain shirt, the price per shirt is modeled by 4.58 times x plus 1073 divided by x plus 128. By the way, I'm going to give you a little, well, no, we'll see this in a second. So let me do this. So I want you to answer these two questions. First off, if you order 20 shirts, find the price per shirt. Once you do that, find the total cost or total price. Did you order 20 and you know your price per shirt, just times that by 20. Does that make sense? I want you to use that equation. Try to type things in your calculator in a way that gives you the price per shirt. And then after you have that, see what. All right. So if you're trying to find the price per shirt, you're going to plug in 20 into that. Some people, again, if you remember learning about function notation. This is f of 20. This is what's the price going to be when you put in an order for 20 shirts. So the price per shirt is going to be 4.58 times 20 plus 1,073. And that's all going to be divided by 20 plus 128. Now, when you do that calculation, you should end up getting $7.87 per shirt. So that's the price per shirt. If you didn't get this, I'll show you in just a second how I'm typing this into the calculator. Because there are multiple ways you can type this into the calculator to figure this out. So I'll show you the easier ways that I know of in just a moment. But before I do, let me finish this by finding the total price. The total price is just going to be the number of shirts times the price per shirt. So I'm just going to take 20 times 787. Is that okay? And when I did that, I got $157 and 40 cents. Is that right? So total price is just 20 times that price per shirt, $7.87. So let me go back to this. If you're not calculating or if you're not getting this the right way, what I like to do is I like to do one of two things. One option is on my calculator, you put parentheses around the entire top, being very careful to only put one parentheses in front of this entire expression and one parentheses behind that entire expression. And then put parentheses around the entire bottom. So that's option one. You put parentheses around the numerator, parentheses around the denominator. Okay. Notice I kind of left off these parentheses because they're not needed for the calculation. So I'll leave those off. Option two is I take my 458 times 20 plus 1073 and I calculate that in one line of my calculator. And I ended up getting 1164.6. And then maybe on another line in my calculator or just in my head, I add 20 plus 128. which becomes 148. So I calculate the top first, then calculate the bottom, and then I divide. I'm rounding that to 2 decimal places because it is a monetary amount. So if you want to do this on one line in your calculator, you have to have parentheses around the entire numerator and the entire denominator. If you're willing to do 2 or 3 lines on your calculator, then you can just calculate the numerator, write it down, calculate the denominator, write it down, and divide. This one is a little more foolproof, where people don't mess up as easy. This one is really easy to put a parentheses in the wrong spot. Again, if you're good at this one, by all means do it. But this one's probably a little bit more foolproof, this version. Is that all right? A little bit easier for most people to do this. But again, either way works. Now, we could do the same for 130 or 1,000 or however many t-shirts we wanted to use. Okay? Let me just for a second, instead of you typing this in, I'm just going to type this in. Do it in there. I just typed in price per shirt if you get 130 of them. Oh, there you go. What if we ordered, let's say 1,000? What if we ordered 10,000? The more and more shirts you order, the lower that price is going. But it's not going towards zero. It's not getting towards zero. In fact, if we went out like millions, you'd see that the price per shirt is really, really close to that 458 number. All right, if you went out to millions. In fact, let me go out and do that once. And go. That's what happens if you order 10 million. Notice that the price is exactly 458 if you order 10 million. So the more and more you order, the closer and closer you're getting to 458. That's the point. Which just happens to be this coefficient divided by the 1 coefficient. Interestingly enough. Right. Now, is this the model that Custom Ink actually uses? Probably not, but it's an interesting one, right? Here's another example of a rational scenario. Oh, we're almost out of time, so I'll just give you the rational scenario and kind of talk through it. This is the amount of medication left in somebody's system, all right? Eventually, it goes down to very, very close to zero, but it takes a while to get there. It's given, the amount after T hours is given by this, 600 divided by 0.4 T plus 1. And once again, we could figure out after 4 hours how much is in the system. Initially, how much is in the system. After 5 days, what would that be? 5 times 24 hours per day. 120 hours. How much is in the system? All right. And that's basically it. So we have this rational model where the amount of medication is going down, getting closer and closer and closer to zero. And it'll essentially be zero at a certain point. And then we could ask questions like, how much is in the body initially? How much is after 2 hours? How much is after 7 hours? Right? Things like that. I won't do those calculations. If you want to do those on your own, again, all you're doing is initially plugging in T of 0. After 4 hours, you're plugging in T of 4. After 7 hours, you're plugging in T of 7. Okay, after 2 hours, T is 2. Any questions about that? So we're given this rational model. And then we're using it for our calculation purposes. All right. Okay. Now, if you want, you can do both of these homeworks right now, the linear exponential homework and the quadratic rational models homework. We'll probably go over the given models at the beginning of next class, and then also get into the chapter 8 material. Other than that, I will see you next time.